Yes, thank you very much. Hello, everyone. I'm going to share my screen right now.
Yeah.
Okay, I'm going to place the presentation.
Yeah, we can see your screen, doctor. Please start your presentation. Hi, doctor. Can you hear me?
Yes.
We can't hear your voice. So, we can't hear your voice in the presentation.
Yeah, the voice is recorded here. Yeah, just a second. I will try to fix the problem.
Yeah.
You can hear me, right? Okay. You can. Actually, I'm playing with Windows Media Player here. To with the voice. Can I stop sharing for a second?
Yeah. Stop sharing your screen once and share it again.
Can you hear it right now?
Yeah, we can hear your voice now.
But you can't hear the presentation?
No. Can you share your screen again? Close the tab and yeah. Okay. Thank you. So when you're there is a check.
Okay.
Yeah, there is a checkbox.
Okay, I guess I knew the problem. I'll share again.
Yeah.
You can hear it now? Can you hear me?
Yeah, we can hear you, but the audio of your presentation is off, doctor.
I see. Is it okay right now? Can you hear it?
Yeah, we can hear your voice now.
Can you hear the voice right now?
Please play your presentation.
Hello, doctor. Can you hear me?
Yes, it seems I can't adjust the sound. Okay, I'll try to fix it and maybe come
Yes,
back. Okay.
doctor.
Okay.
Let me
Thank
help you.
Okay.
When you click on screen share button,
Okay.
on the left side bottom, you will find a checkbox, share
Share
sound.
sound. Okay.
Yes, please click that one. Then select your application, then click on share.
Okay. Okay. Thank you very much.
Properties. I'm Dr. Ehab.
Yes, doctor, we can
Hello
hear you
everyone.
now.
Thanks for
Okay,
introducing me.
that's good. Thanks.
I'm glad to be here with you
Can you
at the
please put it on full screen mode, doctor?
applications
Okay.
and properties. I'm Dr. Ehab
That's
Awad
good.
from the Electrical
Yes,
Engineering
perfect. Thank you.
at
Thank
King
you.
Saud University in Saudi Arabia. My keynote talk today will spotlight some research work on optical metamaterials. I will focus on optical metamaterial applications for nanolasers and spectral reshaping. First of all, I would like to introduce the definition of metamaterial. As most of you already know, metamaterials are artificially engineered materials with arrays of nanoscale unit cells. These metamaterials can interact with light in unusual ways that allow them to have some new and unique physical properties. Here we will focus on optical metamaterials that have nanogaps as unit cells, and we will illustrate two examples of applications. The first example is gain metamaterial that has periodic air gaps across waveguide widths. This metamaterial can be used to build nanolasers that are compatible with silicon on insulator technology. The second example is optical metamaterial with periodic air gaps along waveguide lengths. This metamaterial can be used to reshape propagating light spectrum to have different types of optical filters. Here is our first example, a novel optical gain metamaterial which can be used to build nanolasers. Let's first introduce some of the reported technologies on nanolasers that utilize gaps or slots. Here in this work done by Parius, a micro-ring resonator is made of silicon. The circulating light wave is mainly concentrated within a slot inside the ring waveguide. The slot is filled with an erbium-doped silicon dioxide that is working as a gain medium. The circulating electric field is shown in the inset on right hand side. The ring can work as a light emitting device with a high quality factor, which could be used in lasing application as well. The device is compatible with silicon on insulator technology. It overcomes poor silicon efficiency as an emitter by using a waveguide slot filled with a gain material. Here on the left hand side we have a work done by Liang on a hybrid silicon microring laser. The laser have an indium aluminum gallium arsenide quantum well ring resonator on top of a silicon disk. This structure is bonded on top of a silicon insulator wafer. The lasing threshold is estimated here to be 5.4 milliamps. On the right hand side, we have another work done by Kim on an indium gallium arsenide nanowire array laser, which is built on silicon on insulator platform also. The laser is optically pumped and it has a photonic crystal cavity that has a high quality factor. The confined electric field of the lasing fundamental mode is shown on the bottom figure. Now we move on to our gain metamaterial nanolaser. The GaN metamaterial here consists of alternating indium gallium arsenide phosphide GaN strips and air gaps. Each GaN strip has a width of 30 nanometer, while each air gap has a width of 10 nanometer. The picture on the right shows the refractive index profile of the GaN metamaterial, which is built on top of a silicon dioxide substrate. This GaN metamaterial is separated from input and output waveguides with two air gaps. Each has a 10 nanometer width. The input optical pump has a wavelength of 800 nanometer and the laser has two outputs, which are lasing at 1550 nanometer. That laser is suitable for on-chip optical communication applications. The height of GaN metamaterial and the input and output waveguides is estimated to be 400 nanometer. This device can function as a traveling wave laser with only one single pass inside 3.6 micrometer long GaN metamaterial. Here we characterize the nanolaser GaN metamaterial. The first figure on the left shows the electric field magnitude across the metamaterial waveguide. The field is concentrated inside the 10 nanometer air gaps with evanescent small tails inside the GaN strips. The second figure shows that the metamaterial refractive index depends on the duty cycle of GaN and air strips. This duty cycle can be selected to ensure single mode operation for both pump and lasing modes, in addition to optimize optical pump absorption as well as lasing efficiency. The best duty cycle is found to be 75%. The third figure shows the magnitudes of pump and laser fields along the metamaterial waveguide length. The efficient metamaterial allows to have almost total pump absorption in one single pass, whereas the lasing field reaches its maximum value at 3.6 micrometer length of GaN material. These figures show the electric field distributions at different parts of nanolaser. The variational finite difference time domain is used to simulate these figures. The variational method is used to convert 3D simulations of planar waveguide into 2D simulation, and thus shorten the simulation time and save computational memory. The first figure shows the longitudinal cross-section of the nanolaser. The electric field is concentrated inside air gaps, forming hot spots. There is some little Fabry-Perot multiple reflections at the input and output waveguide, resulting in some ripples in the field distribution. The second figure shows a vertical cross-section in the metamaterial waveguide. The electric field shows a 2D Gaussian fundamental mode of electric field, despite of the gaps across the waveguide width. The third figure shows one of the laser outputs. The laser field maintains 2D Gaussian distribution without any signs of higher order modes. These figures characterize the metamaterial nanolaser performance. The first figure shows the optical spectra of forward and backward laser outputs. The lasing line width here is 0.88 nanometer. The signal to noise ratio SNR is about 51 dB, and the side mode suppression ratio SSR is about 26 dB. The second figure shows the laser output power versus pump power. The laser threshold is around 200 microwatt. The slope efficiency is around 40%. The third figure shows the signal to noise ratio and side mode suppression ratio as a function of pump power. The minimum SNR is about 40%, whereas the minimum SSR is about 25%. Here is a summary of the gain metamaterial nanolaser advantages. First, it's compatible with silicon on insulator technology, and it has a very low optical pump threshold of about 200 microwatt. The pump has a very high absorption efficiency of about 87.5%, and the laser has high internal and external quantum efficiency. The internal efficiency is about 99%, and the external quantum efficiency is about 84%. Also, the nano laser has a very good lasing slope efficiency of about 43% and a narrow line width of about 0.88 nanometer. The laser also has good signal to noise ratio and good sideband suppression ratio. And the laser size is compact with a short lens of about 3.6 micrometer. Now let's move to our second example. It's about a novel optical metamaterial for spectral reshaping of light, which can be used in optical filter applications. First, let's introduce some of the reported technologies for metamaterial filters with embedded gaps or slots. Here in this work, sub-wavelength metamaterial waveguide grating that are loaded with segments can form a high quality factor optical Fabry-Pro filter. The figures on the right show reflectance and transmittance for different metamaterial parameters, which can be used to obtain different spectral bandwidths. Here is another work done by Lu. It shows that cascaded Bragg gratings with different periodicity should be used to obtain more than one Bragg spectrum. In this work, the multiplexing of 4 wavelengths division multiplexing channels is performed as shown in the right figure. Here is our work on partial width entrenched core waveguide. The device has a few mode silicon waveguides surrounded by air. The core width is about 850 nanometer and it's built on top of a silicon dioxide substrate. The waveguide height is 220 nanometer, which makes it compatible with CMOS fabrication technology. The rectangular nano air gaps are entrenched in the middle of the waveguide core. However, their widths partially fill the waveguide, and they are periodic. The waveguide has a transmission output port as well as a reflection output port. The partial width nano gaps cause perturbation and nano-focusing to waveguide propagating modes. The perturbed waveguide fundamental mode result in additional second-order even mode, in addition to the zero-order mode. Each mode suffers from multiple reflections and transmissions through the air gaps. The first graph on the left shows the finite difference time domain electric field profile of the second-order mode, with concentrated fields within the air gaps. The rightmost graph shows the field of the zero-order mode. The middle graph shows the reflected and transmitted spectra due to Bragg grating interference. The first hum corresponds to the second-order mode, while the second hum corresponds to the zero-order mode. The two hums has close separation and different bandwidths, which is unusual for a standard Bragg grating. This video shows the instantaneous evolution of the two modes along the device length. The blue curve corresponds to second order mode, while the red curve corresponds to the zero order mode. The fields are mainly concentrated within the nano gaps, and they spread across the entire core width in between air gaps. The fields are attenuated and almost disappear by the end of the waveguide. In these figures, we characterize the device performance as a function of break period detuning, given that the air gap width is fixed at 50 nanometer and the number of gaps is 30. In the top first figure, the two Bragg resonance wavelengths of humps can be tuned. The dashed line represents each hump boundary, and the difference between dashed lines is the hump bandwidth. As seen in the top second figure, the first hump bandwidth is almost constant, whereas the second hump bandwidth increases because the zero order mode is the most affected one by the period detuning. The top third figure shows that the hump peaks variations are very small, with a peak value of more than 90%. The bottom figure shows that the device dispersion is very small, in the range of few femtoseconds per nanometer. In these figures, we characterize the device performance as a function of gap width detuning, given the break period is fixed at 320 nanometer and the number of gaps is 30. In the top first graph, the two Bragg resonance wavelengths of humps can be tuned. The dashed lines represent each hump boundary, and the difference between dashed lines is the hump bandwidth. As seen in the top second figure, the first hump bandwidth is almost constant, whereas the second hump bandwidth increases, because the zero order mode is the most affected by the gap width detuning. The top third figure shows that the hump peaks variations are very small, with a peak value more than 90%. The bottom figure shows that the device dispersion is very small, in the range of few femtoseconds per nanometer. These graphs show how the gap width and break period can be engineered to reshape the double hump spectrum and thus obtain various optical filters. For the double stop band filter, the first hump reflects both the optical communications S band and C band, whereas the second red hump reflects wide range of shortwave infrared band from 1700 to 1910 nanometer, with a bandwidth of 210 nanometer. The first blue hump reflects both the optical communications E band and S band, whereas the second blue hump reflects a wide range of the shortwave infrared band from 1625 to 1895 nanometer, with a bandwidth of 270 nanometer. For the wide passband filter, the center wavelength is 1556 nanometer with a bandwidth of 200 nanometer and an extinction ratio of 17 dB. For both the narrow passband filter and the notch filter, the two humps are brought very close to each other, so that the transmission region forms a narrow bandpass region, corresponding to a notch within the reflection spectrum. The center wavelength is 1536 nanometer with a bandwidth of 10 nanometer and extension ratio of 30 dB. For the ultra-wide band mirror, the center wavelength is equal to 1565 nanometer with a bandwidth of 530 nanometer and extension ratio of 17.5 dB. Finally, I would like to thank you very much for careful listening, and I'll be glad to receive your questions at any time on this email address. Thanks again.
Okay, thank you everyone.
Thank you for the wonderful speech, Doctor. And
Thanks.
the stage is open for questions now. We assume there are no questions for you as of now. If there are any questions later, we will write back to you regarding those.
Okay, thank you very much.
Thank you once again, Doctor.